Hi there. I'm glad you've wandered into this quiet corner of the night, a little place we keep warm here on Fall Asleep to Astronomy. Outside, the galaxy goes on turning, a slow, patient wheel of stars wrapped around something dark and unseen at its heart. Somewhere in that glowing river lies Sagittarius A, the supermassive black hole we say everything here circles around. But tonight, we're going to follow a softer question. If almost every star in the Milky Way is, in some distant sense, moving around Sagittarius A, then what, if anything, does Sagittarius A itself orbit? Is it truly the still center, or just another dancer in a wider, hidden pattern? We'll take our time with that thought, letting the ideas unfold gently, one by one. And if this kind of sleepy wondering keeps you company, a quiet like and a soft subscribe help others find their way to this same calm. For now, let the question rest beside you like a small, steady star, and we'll drift toward it together, unhurried and warm. There is a place in our galaxy where motion and stillness quietly trade places, where what we thought was anchored turns out to drift. For a long time in modern astronomy, people imagined the center of the Milky Way as something almost sacredly fixed, a perfect reference point that everything else could safely orbit around. At that heart sits Sagittarius A, a supermassive black hole, about 4 million times heavier than our Sun, wrapped in a tangle of stars, gas, and invisible forces. In many minds, it was the one thing that did not move. Stars could whirl, gas clouds could twist, entire spiral arms could slowly turn, but the central black hole was supposed to be the still point in all that motion, the quiet pivot around which everything else danced. That idea felt neat, tidy, almost comforting, a universe where, at least somewhere, there was a true center that simply stayed. But in the early 2000s, a small, persistent whisper began to disturb that picture. Observations hinted that the one thing that should never move was, in fact, drifting. The first clues came from the Very Large Array in New Mexico, a spread of radio dishes laid out under big, open skies. Night after night, year after year, researchers compared radio signals from the region of the galactic core, expecting them to line up perfectly with older measurements, like beads on a perfectly straight string. They did not. The differences were tiny, so tiny they would be invisible to a human eye. Each year, the apparent position of Sagittarius A shifted by just a few tens of microarcseconds. A microarcsecond is such a small slice of angle that it almost defies imagination. If you held a human hair at arm's length, its width would still be thousands of times larger than the angle they were measuring. It was like watching a mountain move one atom at a time, or seeing a lighthouse's beam creep across the sky, slower than the growth of moss. At first, nobody wanted to believe it. The easiest explanation was not that the heart of the galaxy was moving, but that something in the instruments was slightly off. Maybe the antennas were misaligned. Maybe there was a software error, a timing glitch, a tiny miscalibration in the way the signals were being combined. The team checked and checked again. They tested their algorithms, recalibrated equipment, invited other groups to look. Yet, quietly, patiently, the numbers kept saying the same thing. The drift stayed. It showed up in data from other arrays, from other continents, under different skies. The signal of motion did not belong to one telescope or one software pipeline. It belonged to the galaxy itself. That was when the whispers began to take on a different tone. Perhaps the center is not truly still. Perhaps even the heart of the Milky Way trembles. High above Earth's atmosphere, another set of eyes joined the story. NASA's Chandra X-ray Observatory, drifting in orbit, far from city lights and atmospheric blur, watched the black hole in a different kind of light. Chandra's detectors are sensitive to high-energy X-rays, the glow of gas heated to millions of degrees as it spirals close to the black hole's event horizon. By tracing those faint, sharp photons, astronomers could listen to the environment around Sagittarius A in a new way. They found something delicate and surprising. The X-ray emissions were not perfectly steady. There were slight, periodic changes in the patterns of brightness and timing, like a slow, quiet pulse. It didn't look random. When they compared these variations to the known orbits of stars in the region, stars like S2, S29, and S62, they saw a match. These stars, some of them more massive than our Sun, move at astonishing speeds, more than 5,000 kilometers every second, whipping around the black hole like glowing sparks, tracing tight loops in the dark. Each star, in its rush, tugs on the black hole just a little, the way a child might tug on the hand of an adult as they spin together. One star pulls in one direction, another star pulls in another. Over time, these tiny gravitational nudges add up to a gentle wobble, a slow dance of the massive object we once imagined as perfectly fixed. The motion is small, but it is there, delicate, rhythmic, measurable, like the barely perceptible sway of a great tree under the weight of a distant breeze. In 2008, a team at the Max Planck Institute for Extraterrestrial Physics in Germany deepened this picture. Using infrared interferometry, they began a patient, multi-decade project to track the paths of stars near Sagittarius A with astonishing precision. Under the leadership of astronomer Reinhard Genzel, they stitched together light from multiple telescopes, turning distant starlight into a tool for measuring motion down to the width of a pencil tip, seen from thousands of kilometers away. They watched as S2, one of the most famous stars in the region, completed its long, stretched orbit. Every time it swung close to the black hole, racing through its closest approach, the apparent position of Sagittarius A shifted just slightly, but in a way that could be predicted. The black hole did not surge or lurch. It responded subtly to the pull of the star, as if acknowledging its presence with a small, gravitational nod. Years later, Genzel would share a Nobel Prize for the proof that the Milky Way's hidden center truly is a black hole. But for many who followed his work, there was something just as haunting as that confirmation. The realization that this enormous mass, so dominant, so central, still moved in response to its surroundings. He once described it as watching the heartbeat of the galaxy, a vast system expressing its life not through sound or light, but through tiny, measured shifts in position. Behind every one of those measurements lay quiet stories of human patience and care. At the Control Center for Chandra in Massachusetts, engineers learned to align mirrors so precisely that even the faint vibration of a passing truck on a nearby road could smear the data. They built systems to sense and compensate for those tremors, to catch disturbances that would never be felt by a person but would be loud to a telescope listening for whispers in X-ray light. Out in the New Mexico desert, at the Very Large Array, engineers and technicians worked long nights in dry, cold air. They climbed metal ladders to tall dishes, wiped dust from antenna joints, checked cables for tiny imperfections that could introduce static into the signal. A grain of sand in the wrong place, a hairline crack in a connector, could distort the very measurements needed to see the black hole's drift. High in Chile's Atacama Desert, where Alma's 66 dishes sit nearly 5,000 meters above sea level, Teams faced thin air and freezing temperatures. Up there, even simple tasks become slow. Breaths come short, fingers stiffen, and yet the work continues. Adjusting receivers, checking cooling systems, making sure each dish listens with the same care so that their signals can be combined into a single, clear picture. Months blur into years, years into decades, all to track a motion smaller than the width of a human hair as seen from cities away. And yet, that almost imperceptible movement changes everything. It tells us that gravity is not a rigid chain holding things in place, but a web of relationships. No object, not even the most massive one in our galaxy, stands outside that web. Every nearby star, every dense knot of gas, every hidden clump of dark matter adds its own small influence. Together, they push and pull on the central black hole, creating a slow, ceaseless oscillation, perhaps the most subtle motion ever measured in the Milky Way's core. To see this wobble, astronomers rely on one of the most precise techniques humans have ever built: very long baseline interferometry. Instead of using a single telescope, they link many radio telescopes scattered across Earth, from Hawaii's volcanic slopes to the plains of Spain, from the high plateaus of Chile to icy outposts in Antarctica. Each dish listens to the same distant signal, carefully time-stamped by atomic clocks so stable that they drift less than a billionth of a second over years. By comparing exactly when the radio waves from Sagittarius A arrive at each station, astronomers can reconstruct its position in space with incredible accuracy, down to a few micro-arc seconds. It is a kind of planet-sized listening, where distance becomes an ally rather than a limitation. The technique is a quiet triumph of coordination and mathematics, of patient people working across languages, time zones, and climates to act as if Earth itself were one single giant eye. The picture that emerges from all of this effort is not one of stillness, but of constant motion. The black hole that anchors our galaxy's center does not sit like a nail driven into wood. It floats, pulled gently in many directions at once by the surround of stars and matter, even as it pulls them into their orbits. Motion is not something that occasionally happens to it. Motion is the condition it lives in. Further out, another space observatory added its own soft confirmation. ESA's Gaia mission, circling the Sun along with Earth, measures the positions and motions of more than 1 billion stars in the Milky Way. By watching how those stars shift against the even more distant background of quasars' bright, far-off beacons, Gaia revealed how the whole galaxy, including its central black hole, drifts through space. The numbers pointed to a shared motion of about 552 kilometers every second, our entire spiral of stars sailing together through the cosmic dark. So even the center is not truly centered in any absolute sense. It is part of a larger flow, carried along by a bigger pattern of movement. As one astrophysicist once put it, motion is not something that happens in the universe. It is the universe. Everything we see and touch, every orbit and drift, is a thread in that larger fabric of change. In 2022, another milestone made this story feel closer and more tangible than ever before. The Event Horizon Telescope team, a global collaboration using very long baseline interferometry at its most ambitious, released the first direct image of Sagittarius A. It looked like a soft orange ring of light, blurred at the edges, wrapped around a dark center where the black hole hides. To create that image, 8 observatories scattered around the planet had to wait together for the right weather, the right clarity of sky, the right quiet in the atmosphere. When the conditions finally aligned, They recorded petabytes of raw data onto hard drives, physical objects that had to be carried by plane across oceans to central processing centers. There, over more years of work, teams calibrated, cross-checked, and gently coaxed an image out of the noise. When it finally appeared, some of the scientists described the black hole as looking blurry, restless, almost alive. Even in what we call a still picture, there were hints of change, the luminous gas orbiting, flickering, flowing, the whole structure subtly shifting from moment to moment. For the first time, humanity could not only infer the presence of a black hole at our galaxy's center, we could see the glow of matter circling it, feel in the image itself the tension between gravity and motion. It was like watching the heart of the Milky Way breathe, each bright arc of gas a sign of energy being transformed, of orbits unfolding, of time passing in a place far beyond ordinary experience. All of this, the radio drift, the X-ray pulses, the infrared star tracks, the orange ring comes together to whisper the same quiet lesson. That tiny shift in Sagittarius A's position is enough to remind us that even gravity, the strongest large-scale force we know, never creates perfect balance. There is no object so heavy that it can ignore the world around it. Every mass listens in its own way to every other mass. The core of the Milky Way does not stand above this rule. It participates in it. So when you look up at the Milky Way on a clear night, that pale band of light stretching from one horizon to the other, it can be soothing to remember that none of it is truly fixed. The stars you see, the swirling dust, the distant clusters, and the black hole at the center are all moving together, wrapped in the same invisible currents. The sun that warms you, the earth that carries you under its sky, the photons that reach your eyes from that glowing band, all of them are orbiting, drifting, tracing gentle arcs through space and time in response to one shared gravity. The place we once thought of as the most stable point in our galaxy turns out to be one of the most quietly alive, shifting just enough to reveal how deeply it is connected to everything around it. In that subtle, almost secret motion lies a deeper mystery, one that asks what happens when we follow that chain of movement all the way out, and wonder what, if anything, the center itself might be circling. If the very center of the Milky Way can wobble, even just a little, it's natural to wonder what keeps it from drifting off altogether. If Sagittarius A shivers because of everything that surrounds it, then what, if anything, holds it in place? The question sits there quietly, like a stone dropped into deep water, and the ripples lead us toward the next layer of the story. Sagittarius A, the supermassive black hole at our galaxy's heart, is unimaginably heavy. It holds about 4 million times the mass of the Sun in a region smaller than the orbit of Mercury. Its gravity bends light, slows time, and shapes the paths of billions of stars. In the grand architecture of the Milky Way, it is one of the most dominant presences we know. And yet, even this immense anchor is not perfectly still. It quivers. This faint motion, this gravitational wobble, is one of the most delicate motions ever measured in astronomy. To uncover it, people had to design an experiment that would stretch not just our technology, but our patience. In the early 1990 seconds, a small group of astronomers at the European Southern Observatory decided to spend years, and then decades, simply watching the stars near the galactic center. At that time, Sagittarius A was mostly just a bright, compact radio source on their maps. Its true nature was suspected, but not yet proven. Its edges couldn't be seen, only inferred. The plan was simple in idea, but demanding in practice. Track the stars around this bright point and see how they move. If their orbits behaved as if they were being pulled by something extremely massive and concentrated, that something would almost have to be a black hole. Among those stars, one in particular began to stand out. We now call it S2, a hot, blue-white giant, about 15 times the mass of our Sunday. S2 moves at a speed that feels almost impossible to imagine, up to about 7,600 kilometers every second when it rushes closest to the center. Unlike our Sun, which takes hundreds of millions of years to orbit the galaxy, S2 completes a full loop around Sagittarius A in just about 16 years. On cosmic timescales, that's a blink, a single breath. Each time S2 swings through its closest point to the black hole, its path curves sharply, like a comet being whipped around an invisible sun. In 2002, as S2 reached one of these close passes, telescopes on Earth watched its speed spike, just as gravity predicted it should if an enormous mass was lurking at the center. That moment was a quiet turning point. The star's motion was so extreme, and the region it swung around so small, that there was really only one explanation. Astronomers could finally say with confidence that the Milky Way's center was home to a supermassive black hole. The calculations, the orbits, the observed speeds, they all converged on the same conclusion. What had been a suspicion became a measured reality. But as the observations continued, something more subtle began to appear. When researchers refined their measurements, they noticed that the central point itself was not perfectly fixed. As S2 sped past, the apparent position of Sagittarius A shifted just a little, as if the black hole were being nudged by the very star it was controlling. The effect was tiny, almost swallowed by noise, but it was there, repeating in a way that was hard to dismiss. To see such a small motion, scientists relied on interferometry, a technique that merges the light from multiple telescopes to act as though they were a single, much larger mirror. By aligning signals from observatories like the Very Large Telescope in Chile, Keck in Hawaii, and later an instrument named Gravity on the Very Large Telescope Interferometer, they could pinpoint the position of S2 and its neighbors with astonishing precision down to a few tens of microarcseconds. A microarcsecond is such a small angle that comparisons start to sound like poetry. One common way to picture it is to imagine placing a coin on the surface of the moon and then trying to detect its motion from Earth. That is roughly the level of subtlety we're talking about. Yet, in that realm of almost impossibly fine detail, the orbits of the stars became maps. Each star traced out an invisible pattern in space-time around Sagittarius A. And when scientists laid all those patterns together, the center point, the place that should have been perfectly still, shifted slightly from where a motionless object would sit. One of the first to frame this behavior in simple, clear words was Andreas Eckert from the University of Cologne. He described the effect by saying that the black hole wasn't being moved by much, but it was being moved by something. That something turned out not to be one star, but the combined influence of a small cluster of massive stars very close to the galactic center. Roughly 30 to 40 of them, many dozens of times heavier than the Sun, swirl around in that region like bright embers caught in a powerful whirlpool. Each of those stars exerts its own gravitational pull on the black hole. Alone, the effect would be tiny. Together, over thousands of years, their combined tug is enough to make even a 4 million solar mass black hole sway by a fraction of an astronomical unit. The numbers suggest a drift on the order of about 0.2 astronomical units, or so, the kind of distance that separates the Sun from Mercury. spread over timescales too long for any single human lifetime to witness directly. But the mathematics and the careful measurements say that sway is real. To picture it in a gentler way, you can imagine a heavy buoy floating in a restless ocean. The buoy represents the black hole. The waves are the gravity of the surrounding stars. No single wave is strong enough to shove the buoy far from where it is, but together, they keep it in constant, mild motion. It rocks, drifts, leans one way, then another, always responding to the pattern of waves around it. That is how Sagittarius A stays in place, not by being truly immobile, but by being caught in a balance of motions that nearly cancel out. From far away, that buoy looks steady. From far away, the black hole seems fixed, the stable center of a spinning disk. But when you look more closely, with instruments sensitive enough to catch even the faintest sway, you find that what we call stillness is simply motion that is symmetrically arranged. It appears stable because every force is matched by another. Every pull is balanced by an equal, opposite tug. The calm you see is the surface of a very precise, ongoing negotiation. The data that revealed this subtle balance came from some of the most advanced instruments ever pointed at the sky. On the high summit of Cerro Paranal in Chile, the very large telescope's 4 main mirrors sit in a row, each within its own dome. The gravity instrument was designed to combine their starlight so they could function as a single, virtual telescope with a resolution about 1,000 times finer than Hubble's. To make that work, engineers had to guide beams of infrared light through tunnels, mirrors, and delay lines with microscopic accuracy. In 2018, gravity did something beautiful. By watching S2 complete another close pass around the black hole, it detected tiny redshifts and blue shifts in the star's light. Redshift when the star moved away, stretching its light, and blue shift when it moved toward us, squeezing its wavelengths shorter. These subtle shifts matched the predictions of Einstein's general relativity, not just the Newtonian pull of gravity, but the extra curvature of space-time close to something so dense. It was like seeing theory and reality gently clasp hands. Hidden inside those same observations, however, was another quiet detail. When S2 came near, the inferred position of Sagittarius A shifted just the smallest bit in the opposite direction, as if the star and the black hole were sharing a gravitational handshake. For the first time, we were not only seeing a star respond to a black hole's pull, but a supermassive black hole physically respond to the presence of a nearby star. Frank Eisenhower, one of the key figures behind the Gravity Project, described the feeling of seeing that motion as being like watching the black hole breathe. To reach that moment, he and his colleagues had to spend years merging data from telescopes scattered across continents, aligning them in time with atomic clocks so precise they lose less than a second over millions of years. They had to learn to correct the distortions of Earth's atmosphere in real time, using adaptive optics systems that gently reshape mirrors to cancel out the blurring effect of turbulent air. All this effort, all this coordination, just to track a flicker, just to confirm that even the mightiest object in our galaxy can be moved ever so slightly by the company it keeps. And S2 is not the only partner in this dance. Other stars, like S62, move even faster and even closer to the black hole. S62 is believed to complete its orbit in only about 9.9 years, making it the fastest known star in the immediate neighborhood of Sagittarius A. At its closest approach, it reaches speeds of nearly 8% of the speed of light, around 24,000 kilometers every second. At that velocity, gravity's handshake becomes even firmer, and the star's influence on the black hole, though still tiny, compared to the black hole's own mass, is impossible to ignore in the equations. To describe this precisely, scientists use refined versions of Einstein's equations, called post-Newtonian corrections, which take into account both the familiar pull of gravity and more subtle relativistic effects that become important near extreme masses and high speeds. Each time a star like S2 or S62 rushes past, it adds a small twist to the black hole's motion. Over many encounters, those twists stack into a faint but persistent rhythm, like a heartbeat hidden deep within the galaxy's core. Of course, when measuring something this delicate, the first suspicion is always that the effect might be an illusion. Maybe it's a calibration issue, a quirk of the atmosphere, a systematic error in the instruments. To rule that out, teams compared their results with observations from independent telescopes, Keck on Mauna Kea in Hawaii, the Subaru telescope on the same mountain, and other instruments watching the same stars from different angles under different conditions. The wobble was there, again and again. Different mirrors, different detectors, different software pipelines, and yet the same tiny drift in the central point showed up. When your tools disagree, you blame the tools. When they all agree, softly, over many years, you start to accept that the universe is telling you something true. The implications of this are gentle but profound. This tiny wobble reveals how gravity threads through everything from stars to black holes, from bright orbits to the invisible fabric in which those orbits are drawn. It whispers that no object, however massive, is truly separate from the network of forces around it. Each star, every gas cloud, every parcel of dark matter contributes its own small pull. What looks like a solitary center is really a participant in a grand, interconnected equilibrium. In that sense, what holds the black hole still is not a single dominating force, but the sum of countless invisible hands. Every direction you look, something is pulling, and together those pulls nearly balance. The result is not absolute stillness, but the quietest possible motion, a drifting that is always being gently corrected, a center that is always being recentered. Perhaps the most delicate ingredient in this entire discovery was not the technology, but the willingness to wait. To see a full orbit of S2, astronomers had to follow it for 16 years. To understand S62's path, nearly a decade more. The people involved had to accept that the story they were reading would unfold over a large portion of their own lives. They had to resist the urge to force a conclusion too soon, and instead let nature reveal its pattern at its own unhurried pace. When those patterns finally lined up, when orbits closed, data sets overlapped, and instruments matured, the picture that emerged was not one of chaos, but of harmony. A balance so fine that the only stillness the galaxy can offer is this, a state where every movement is answered by another, every tug met by a countertug, and the center appears calm only because its rest is made of motion. Neil deGrasse Tyson once remarked that the universe is under no obligation to make sense to us. And yet here, in this quiet corner of astrophysics, it does. The drift, the wobble, the dance of stars and black hole all fit neatly into the framework of general relativity, a theory written down long before we had the means to test it so precisely. What once might have felt like a paradox, a moving center, turns out to be exactly what gravity predicts. So as you listen, you might picture this, about 26,000 light-years away, in a region you can't see with your eyes. A star like S2 races through space. Its light bends and stretches as it sweeps past the black hole. In that moment, Sagittarius A leans ever so slightly toward it, acknowledging the pull, giving just a little, and then, as the star moves on, slowly drifting back. The motion is too small for human senses to notice, but it is enough to echo through the structure of the galaxy. In that subtle give and take, in that shared sway between star and black hole, you can feel one of gravity's most elegant truths. Once you've seen that even a supermassive black hole can be gently shifted by the company it keeps, an even softer thought begins to form. If nothing at the heart of our own galaxy is truly still, then what, if anything, can ever be called the center of anything larger? If Sagittarius A wobbles because everything around it tugs and whispers, what, in turn, steadies Sagittarius A? And if that can move, then what do we really mean when we talk about the center of the universe at all? The answer begins with a simple but quietly powerful idea. Nothing holds still because everything holds everything else. Every mass, every star, every cluster, every cloud of dark matter participates in a shared balance. There is no single object that gets to sit at the perfect middle and watch everything else go around. Instead, there is an invisible point, a kind of shared center of gravity, defined not by one thing but by all things together. Astronomers call this kind of shared balance point a barycenter. It's not a physical object you could visit. It's a location in space where, if you could magically put a scale there, the pull of all the masses around it would cancel out. You've already seen a small version of this in your own cosmic neighborhood. Earth and the Moon do not orbit with Earth perfectly fixed and the Moon simply circling it. Rather, both of them orbit their common barycenter, a point that happens to sit a little beneath Earth's surface because Earth is much more massive. The motion is so lopsided that we talk as if the Moon goes around us, but in truth, both bodies dance around a point in between. The same is true of the Sun and its planets. Strictly speaking, the Sun doesn't sit dead still in the middle, while the planets loop around in neat, isolated paths. The entire solar system orbits its own barycenter, which shifts around depending on where the giant planets like Jupiter and Saturn happen to be. Sometimes that barycenter lies just inside the surface of the Sun, sometimes just outside. The Sun itself wobbles ever so slightly as those planets move. Now extend that idea outward. Think of the Milky Way as a vast, luminous disk about 100,000 light years across. Spiral arms unwind like slow, glowing streams. Billions of stars drift and orbit, some in tight circles, others in more oval paths. Clouds of gas and dust coil and stretch. A giant halo of dark matter surrounds everything, invisible but heavy. Near the seeming center of this swirl sits Sagittarius A, enormous and intense, shaping the orbits of stars in its immediate neighborhood. For a long time, it was tempting to imagine that Sagittarius A was the ultimate anchor of this whole system, the one fixed point in the Milky Way's gravitational story. But as our measurements became sharper, something more nuanced came into focus. The black hole itself is part of a bigger orbit, a larger pattern of motion that includes not just nearby stars, but the entire galaxy. The true balance point, the Milky Way's barycenter, is defined by all of its mass together: the stars, the gas, the dark matter, and yes, even tiny pieces of matter like you and me. On this scale, Sagittarius A is not an immovable nail hammered into the fabric of space. It's one of the heavy dancers in a crowded hall, moving as everyone else moves, pulled and corrected by the collective gravity of billions of companions. The center of the galaxy's mass is not exactly where the black hole sits, It's a point determined by the combined distribution of everything, and the black hole orbits that, just as the stars orbit the black hole. And even that is not the end of the story. When we zoom out further, we find that our galaxy itself is in motion, sliding through space relative to a background that carries its own faint memory of the universe's beginning. NASA and ESA have helped trace that motion with a set of quietly astonishing observatories. ESA's Gaia mission set out with a simple instruction that hid a deep ambition: map the positions and motions of more than 1 billion stars with accuracy better than 1,000th of a degree, and do it again and again over years. By comparing how those stars shift against one another over time, Gaia could not only reveal the internal flows of the Milky Way, but also how the entire galaxy is drifting relative to more distant beacons. At the same time, satellites like NASA's WMAP and later ESA's Planck turn their attention to something even more ancient: the cosmic microwave background. The faint afterglow of the Big Bang. Spread across the sky, this glow is almost perfectly uniform, a nearly constant temperature in every direction. If we were sitting truly at rest with respect to this relic light, the map of its temperature would be almost perfectly smooth, with only tiny ripples left over from the universe's earliest structure. But when WMAP and Planck looked, they found a clear pattern. One side of the sky appeared slightly warmer, the opposite side slightly cooler. This is called a dipole, and its most natural explanation is beautifully simple. If you move through a sea of light, the photons you're moving toward get slightly boosted in energy, appearing a touch warmer, while the photons behind you get slightly stretched, appearing a bit cooler. Just as the pitch of a siren changes as it passes you, the pitch of the microwave background changes for a galaxy in motion. From that subtle, warm, cool difference, scientists could calculate how fast and in what direction we are traveling through this ancient light. The numbers point to a speed of around 552 kilometers every second in a direction roughly toward the constellation Leo. That translates to nearly 2 million kilometers every hour, a quiet, persistent glide through space. Gaia's star motions and Planck's sky map, built on completely different methods and different kinds of light, both converge on the same story. We are not simply spinning in place. The Milky Way is flowing. That word flowing captures something that falling into does not. We are not plunging straight into a single point, so much as participating in a broader current. Our galaxy, with its black hole, its spiral arms, its gas, and its planets, is moving within a cluster of more than 50 galaxies, known as the local group. This group includes our neighbor Andromeda, M31, the Triangulum Galaxy, M33, and many smaller companions. The gravity of all these galaxies, along with the dark matter that threads between them, defines another barycenter, another shared balance point. The Milky Way and Andromeda, in particular, are on a slow collision course, approaching each other over billions of years. Their mutual gravity helps define the motion of the entire local group. But even the local group does not live in isolation. It is part of a larger arrangement called the Virgo Supercluster, a vast region filled with clusters of galaxies, and that, in turn, is wrapped inside an even grander structure that astronomers call Laniakea, a sprawling network of galaxies and dark matter flowing together over hundreds of millions of light years. Each of these levels has its own balance point, its own version of a barycenter. The Milky Way orbits the local group's barycenter. The local group moves within Virgo's gravitational landscape. Virgo and its neighbors drift within Laniakea, and all of it moves against the background of the cosmic microwave glow. Motion nests within motion, like shells inside shells, all the way up and all the way down. To see these flows clearly, astronomers have spent years compiling what are sometimes called cosmic velocity maps. Using radio interferometry, they listen to the whispers of hydrogen gas spread between stars, mapping how its emission lines shift as the gas moves toward or away from us. Using masers, natural microwave lasers produced in dense star-forming regions, they measure precise velocities of clouds and clumps scattered across the Milky Way. Gaia's Data Release 3 added another layer, charting the three-dimensional motion of stars across the sky. A 2019 study from the Harvard-Smithsonian Center for Astrophysics used maser emissions from star-forming regions spread throughout the galaxy to refine our understanding of how the Milky Way moves relative to its surroundings. By looking at tiny Doppler shifts, changes in the frequency of radio waves, they could trace not just how gas swirls inside our galaxy, but how the whole system drifts toward a particular region of space. Their results pointed toward a gravitational convergence zone, a kind of deep valley in the universe's mass distribution, sometimes loosely associated with what we call the Great Attractor. When scientists in a quiet lab at NASA's Goddard Space Flight Center compared Gaia's measurements of stellar motions with Planck's map of the cosmic microwave background dipole, the pieces slid together. Two completely different windows onto the sky, one watching stars, the other watching ancient light, both said the same thing. The Milky Way's center is not fixed. It is orbiting an invisible point of equilibrium shared with its neighbors, stitched into a larger web of gravity and dark matter. Behind every neatly drawn velocity arrow and every contour on those cosmic maps are people who spent years and years refusing to accept simple stillness as the default explanation. They checked their instruments against themselves and against one another. They worried about subtle biases in detectors, about the influence of cosmic rays, about calibration drifts that might masquerade as motion. They waited for more data, more time, more orbits, letting the universe speak slowly in its own careful way. As the evidence accumulated, the patterns that emerged told a gentle, coherent story. The universe behaves less like a set of separate objects arranged on a fixed stage, and more like one vast, interconnected system. Every piece influences every other piece to some extent. There is no absolute center where motion simply stops. There are only balances, barycenters defined by relationships. Carl Sagan once reminded us that we live on a small planet, circling an ordinary star, drifting between two minor spiral arms of a galaxy that is itself just one of many. On some days, that can sound like an invitation to feel small, but seen from another angle, it becomes something warmer. Even that insignificant place is part of a choreography grander than any one mind can hold all at once. Our galaxy's center wobbles under the pull of nearby stars. The galaxy itself orbits within the local group's shared gravity. The local group flows within larger structures, all drifting together within the invisible architecture of space-time. What seems still from one perspective is revealed as motion when we step back, and that motion, in turn, sits inside something larger. In the quiet of the night, it can be strangely comforting to know that there is no lonely, isolated center, only a universe where everything moves with and because of everything else. If Sagittarius A isn't truly the center, if it too is being guided by the soft pull of something larger and unseen, then a deeper question begins to unfold. What exactly holds the Milky Way in its vast path? What kind of invisible structure can keep entire galaxies moving as if they were pearls sliding along a thread? It's a question that doesn't just move the black hole. it gently rearranges our sense of where we are. Because once you zoom out far enough, the picture shifts. The Milky Way, with its billions of stars, planets, and nebulae, isn't hanging motionless in space like a painting on a wall. It's moving fast. Careful measurements from ESA's Gaia mission and NASA's Planck satellite tell us that our galaxy is racing through the universe at close to 600 kilometers every second, heading roughly toward the Virgo cluster, a massive gathering of galaxies, more than 50 million light-years away. That's over 2 million kilometers every hour. In the time it takes to listen to a handful of sentences, the entire Milky Way has already slipped hundreds of kilometers farther along its path. But how can we know that something as enormous as a galaxy, 100,000 light-years across, is moving at all? From inside it, everything feels steady. The stars rise and set. The constellations shift almost imperceptibly over human lifetimes, and the band of the Milky Way arches across the sky as if it has always been there. To sense the motion of the galaxy itself, we have to listen to something that fills all of space, something that can act as a quiet reference frame. That something is the cosmic microwave background, the faint afterglow of the Big Bang. This radiation washes over the universe in every direction, a cool bath of microwave light that is almost perfectly uniform. If our galaxy were truly at rest with respect to this ancient glow, the temperature of that background would look the same no matter where we pointed our instruments. But when satellites like WMAP and Planck mapped it with great care, they found a small but telling pattern. One side of the sky appears slightly warmer, and the opposite side slightly cooler. This effect, called the CMB dipole, is like the hum of motion recorded on the universe's oldest film. Just as a car driving through rain feels more drops on its windshield than on its rear window, a galaxy moving through this sea of light feels a gentle headwind of higher energy photons in the direction it's traveling. From the size and orientation of that warm, cool pattern, scientists can work out not only that we are moving, but how fast and in which direction. The numbers that fall out of those calculations are remarkably consistent. They tell us that the Milky Way, along with its neighbors, is moving at about 552 kilometers per second relative to the cosmic microwave background. And it's not moving alone. The entire local group, our cluster of more than 50 galaxies, including Andromeda and Triangulum, is streaming in roughly the same direction, like a flotilla of ships carried along by a broad, invisible current of gravity. To understand what might be pulling us, we have to look beyond the familiar shape of our spiral arms and out into the deep structure of the universe. When astronomers mapped the motions of galaxies in our region, they noticed something puzzling. On large scales, galaxies should, on average, be drifting away from one another as the universe expands, a pattern known as the Hubble flow. But in our corner of the cosmos, the motions weren't perfectly smooth. Many galaxies, including our own, seemed to be converging toward a particular region in the sky. This region lies in the direction of the constellations Centaurus and Norma, and over time, it became known as the Great Attractor. The name itself carries a certain quiet drama, something out there, massive enough to bend the motions of entire clusters of galaxies. When the idea first emerged in the 1980 seconds, it was deeply confusing. Telescopes pointed toward that part of the sky saw very little. The line of sight lay behind the dense plain of our own Milky Way, a zone astronomers sometimes call the zone of avoidance, where thick clouds of gas and dust block visible light. But people kept looking, using tools that could see what our eyes cannot. Radio waves slip through much of that dust. Infrared light can pick out the glow of galaxies hidden behind the Milky Way's clouds. X-ray observatories reveal hot gas in enormous clusters of galaxies. Slowly, through these different windows, a picture began to emerge. The great Attractor region wasn't empty at all. It was rich, full of clusters upon clusters of galaxies, extended over hundreds of millions of light years, all drifting in roughly the same direction, toward the same gravitational basin. One of the most striking advances came in 2014, in work led by Brent Tully and his colleagues at the University of Hawaii. By gathering redshift data measurements of how galaxies' light stretches as they move through space from thousands of galaxies, they built a three-dimensional map of cosmic flows in our local universe. What they found was that the Great Attractor was only a part of a much larger entity, a sprawling supercluster they named Laniakea, a Hawaiian word that can be translated as immense heaven. Laniakea is like a vast continent of galaxies, containing over 100,000 of them. Rivers of galaxies flow along filaments of dark matter, funneling toward deep gravitational valleys. Our Milky Way is just one spiral on one of the smaller branches of that continent, moving with Andromeda and the rest of the local group along pathways defined by mass we mostly cannot see. Tully described the situation in a gentle, memorable way. We are not simply falling into something. We are flowing along the contours of a gravitational landscape. When you pause to consider the layering of all this motion, the scale becomes quietly dizzying. Our solar system orbits the Milky Way's center, taking about 230 million years to complete one full circuit. As it does, the Milky Way itself is drifting with the local group toward the Virgo cluster, following the pull of mass spread over tens of millions of light years. That entire motion is embedded within Laniakea, which itself seems to be drawn by yet another, even larger concentration of matter farther away. Motion inside motion. Orbits nested within flows, like a set of gently turning gears stretching out beyond what we can easily imagine. Behind these sweeping ideas are long years of careful, patient work. At ESA's European Space Operations Center in Darmstadt, teams working on Gaia had to measure the positions and motions of stars with exquisite precision, while their own spacecraft circled the Sunday. Gaia itself has tiny orbital wobbles, thermal expansions and contractions, small vibrations from shifting hardware. Any of these effects, if not accounted for, could be mistaken for motions in the stars it was watching. Engineers and scientists developed algorithms that learn the spacecraft's quirks, subtracting out its dance so that the true motion of the stars could shine through. Over time, this produced catalogs so detailed that we could see stars thousands of light years away, drifting by just a few hundred micro-arcseconds per year. When those stellar motions are combined with redshift surveys and maps of the cosmic microwave background, a coherent picture of galactic motion emerges. We're no longer guessing. We're tracing the Milky Way's trajectory, the way you might trace the path of a ship across a calm sea by watching distant lighthouses slide across the horizon. It's a picture that quietly contradicts our intuition. When you step outside on a clear night and see the Milky Way stretching from one edge of the sky to the other, it feels timeless and still. The idea that, even as you stand there, the entire galaxy is gliding through space, stretching the fabric behind it and plowing gently through the sea of ancient light, is almost too large to hold. Yet every photon you see from that glowing band was emitted by stars riding on that immense journey, carried along without ever stepping off the ship. Even our own sun, which seems so steady and fixed in your daily sky, is part of this multi-layered voyage. It orbits the galactic center at roughly 200 kilometers per second, circling in a path defined by the combined gravity of stars gas, dark matter, and the central black hole. While it does that, the whole galaxy drifts through intergalactic space, with no up or down in any absolute sense, only directions defined by motion and the gentle curvature of space-time itself. In 2020, data from NASA's Cosmic Flows 3 project sharpened the details even more. By compiling distances and redshifts for over 18,000 galaxies, astronomers were able to see how each one moves relative to the overall expansion of the universe. Embedded within the outward Hubble flow, they found streams coherent motions of galaxies toward particular regions. The Milky Way, it turns out, is heading not only toward the Virgo cluster, but also slightly offset toward the Shapley Supercluster, an even more massive concentration of galaxies farther out. It's a bit like realizing that the Great Attractor itself is being pulled by something larger, that the valley we thought was the bottom of the landscape is actually on the slope of a deeper valley still. Gravity, on these scales, is like a web of subtle inclines, guiding galaxies along pathways we can only fully appreciate when we step far enough back and wait long enough. Neil deGrasse Tyson once said that we are part of this universe, and that the universe is in us, that beyond just existing within it, we carry its story in our very atoms. Here, in the quiet motion of galaxies, that thought takes on a literal shape. Every atom in your body, every star you've ever wished on, every galaxy you've ever seen in a photograph is participating in the same grand flow. Not a chaotic scramble, but a deeply connected movement shaped by the unseen architecture of space-time. And yet, as comforting as this coherence can be, the data also leaves us with a new question that feels a little like a whisper at the edge of hearing. If the Milky Way and its neighbors are all streaming in a particular direction, what exactly is doing the pulling? Is it a cluster of galaxies hidden behind thick bands of dust and gas, beyond the reach of our current telescopes? Is it a massive concentration of dark matter, invisible to all forms of light, yet unmistakable in its gravitational influence? Or could it be something even more subtle? A curve in the cosmic web itself, a deeper feature of how matter and space-time arrange themselves on the largest scales? Whatever the ultimate source, we are part of that motion, bound into it by the laws of physics, not by any decision we make. The galaxy moves not because it chooses to, but because the universe is expanding and curving under the weight of mass and energy, seen and unseen. Every orbit, every slow drift, every slight gravitational tug is another thread tying us to that same vast pattern. Even as these words settle in your mind, the Milky Way has already moved a little farther along its path, carrying the sun, the earth, and you with it. Thinking of our galaxy, not as a static pinwheel of stars, but as a vessel gliding through an ocean of gravity, can gently reshape what here means. Sagittarius A is not the final center of stillness. It is one more passenger in a current that carries entire galaxies. And if that is true, if even the galaxy itself is being drawn through space by something larger, then it's hard not to wonder what else might be tugging at everything we know. Somewhere beyond our current maps, beyond the edges of our deepest surveys, that question waits, quiet and patient, like a distant shoreline we can feel in the pull of the tide long before we ever see it. That distant shoreline we can't yet see, the thing we only feel as a gentle pull in our data, has a name. Astronomers call it the Great Attractor. The words sound dramatic, almost like something from a story, but behind them is a very real puzzle. What could be powerful enough to tug on thousands of galaxies at once, including our own? and bend their paths across hundreds of millions of light years? This isn't just a poetic curiosity. It's one of those questions that sits heavily in modern cosmology, a quiet, persistent mystery. Even NASA once described it as an invisible gravity well in the fabric of the cosmos, something so massive that space itself seems to be sloping toward it. And yet, for a long time, we couldn't see it at all. The region of sky where the Great Attractor seems to lie is roughly 150 to 250 million light-years away, in the direction of the constellations Centaurus and Norma. Unfortunately for us, that part of the sky is almost exactly where the thickest band of our own Milky Way crosses our line of sight. Stars, gas clouds, and dust pile up there, turning that area into a crowded, glowing fog. Astronomers have a soft name for it, the zone of avoidance, not because they want to avoid it, but because ordinary optical telescopes struggle to see through it. It's as if the universe has drawn a curtain of starlight and dust right across the place where something important is happening. The first hints that something strange was hiding behind that curtain appeared in the 1970 seconds. Astronomers were measuring the redshifts of nearby galaxies, how much their light is stretched as the universe expands. According to the standard picture of expansion, galaxies on large scales should move away from each other in all directions, with speeds roughly proportional to their distance. The farther they are, the faster they recede. This simple pattern is known as Hubble's law, but when the measurements were plotted, the pattern wasn't perfectly clean. Entire clusters of galaxies, including our own local group, seemed to share an extra motion. They weren't just drifting apart with the general expansion. They were also streaming toward a particular region of space, as if some enormous mass were pulling on them, in addition to the overall expansion. At first, it was easy to suspect mistakes. Maybe there were biases in the sample, or errors in distance estimates. Maybe the galaxies chosen just happened to line up in an unfortunate way. But as the data became better and more numerous, the trend refused to go away. In 1986, two researchers, Donald Lyndon Bell and Sandra Faber, working with a team, published results from a major survey of more than 400 galaxies. Their analysis confirmed a large-scale flow of matter in the direction of Centaurus. Something unseen, vast, and heavy seemed to be tugging on entire clusters. They gave that unseen source of gravity a name that captured both its mystery and its influence: the Great Attractor. From that point on, astronomers around the world began trying to map this hidden structure. But the zone of avoidance remained a serious problem. Optical telescopes, those that use visible light, could barely peer through the dense band of our own galaxy. It was like trying to study a mountain range on the far side of a city by looking through the city's brightest, busiest streets. The foreground glare drowned out the background. So researchers turned to other kinds of light. Radio waves can pass through much of the interstellar dust that blocks optical light. Infrared light can reveal the warm glow of stars and galaxies hidden behind cooler clouds. X-rays can pick out hot gas trapped in the deep gravity wells of galaxy clusters. Each wavelength offers its own way of slipping past the obscuring fog. In the 1990 seconds, the Parkes Radio Telescope in Australia began a project called the High Parkes All-Sky Survey. It used radio waves with a wavelength of about 21 centimeters, emitted by neutral hydrogen gas, one of the most abundant elements in the universe. These waves pass through dust almost as if it isn't there, carrying information about galaxies that would otherwise be invisible to us. Slowly, as the radio data accumulated and were carefully processed, a picture began to take shape. Behind the thick band of our galaxy, in the direction of Norma, lay an enormous concentration of matter, the Norma cluster. Thousands of galaxies packed into a relatively small region, all held together in a deep gravitational knot. And this cluster appeared to be part of a larger, overdense region, the core of what we had been calling the Great Attractor. The discovery was sobering and beautiful at the same time. The Great Attractor was not a single object, not a lone monstrous galaxy, or a mysterious black hole swallowing everything. It was a region of heightened density in the cosmic web, a place where filaments of galaxies and dark matter meet, where the gravitational landscape dips enough to bend the paths of galaxies and slowly deflect the smooth outward flow of cosmic expansion. As time went on, data from missions like Gaia and from surveys such as NASA's cosmic flows reinforced this picture. The motions of galaxies, when measured carefully and corrected for the general expansion, showed a consistent pattern. Our Milky Way and its neighbors are traveling at nearly 600 kilometers per second toward a broad gravitational basin in the sky. The Great Attractor is part of that basin, but not the whole of it. Beyond it lies something larger still, the Shapley Supercluster, a massive assembly of more than 8,000 galaxies, with a total mass estimated at around 10 quadrillion times the mass of the Sunday. In a way, the Great Attractor may simply be the nearer edge of this even grander structure, the visible slope of a deeper valley in the cosmic landscape of mass and gravity. When scientists talk about these flows, they often borrow the language of fluids. Galaxies do not simply shoot like bullets through empty space. They follow the contours of an invisible terrain, gliding along the valleys and sliding down the slopes carved by gravity. NASA astrophysicist Yehuda Hoffman once described it like this: galaxies aren't just flying apart with the expansion, they are also being pulled along the valleys and slopes of the cosmic web. In that web, the Great Attractor behaves like a deep valley, an unseen sinkhole in the distribution of matter, drawing not only galaxies, but the very pattern of space-time into motion. To get a sense of the scale, you can let your mind step through the nested motions again. Our Sun orbits the Milky Way once every 230 million years or so. As it does, the Milky Way drifts over billions of years toward the region of the Great Attractor. Each slow rotation of our solar system, each quiet orbit of Earth around the Sun, takes place inside that larger, almost imperceptible drift. We're not perched above the river watching it flow. We are bobbing in it, carried along. The way we came to map that river is itself a gentle story of persistence. In 2016, an international team led by Hélène Courtois at the University of Lyon used the Cosmic Flows 2 survey to measure the velocities of more than 8,000 galaxies in 3 dimensions. They weren't just interested in how far away those galaxies were, but in how each one moved relative to the overall expansion of the universe. To tease out the underlying pattern, they applied a mathematical technique called Wiener filtering, an approach that helps separate signal from noise, removing random motions to reveal the smoother, large-scale flow beneath. The result was a kind of topographic map of the local universe, not in terms of mountains and rivers, but in terms of gravitational basins and streams of galaxies. The map showed long filaments of galaxies flowing together into an enormous basin they identified as Laniakea, our home supercluster. Within that basin, the Great Attractor emerged as a central node, a deep part of the gravitational network where flow lines seemed to converge. Courtois summed up the feeling in a simple phrase: our home is much bigger than we thought. Suddenly, home didn't just mean the solar system, or even the Milky Way, but a sprawling region of space hundreds of millions of light years across, all connected by the shared motion of galaxies. Each point on that map, each glowing speck representing a galaxy, rested on countless hours of observation. Data from dozens of observatories had to be synchronized, corrected for Earth's motion around the Sun, for the Sun's motion around the galaxy, for the galaxy's motion through the cosmic background, and for relativistic effects that subtly alter light at high speeds and great distances. Behind every pixel lay not only the light of distant galaxies, but also years of quiet work at computers and telescopes, people checking and rechecking to make sure that the patterns they saw were truly cosmic and not artifacts of their instruments. Even with all that effort, the mystery is not finished. The deeper we look, the more motion we find. When the James Webb Space Telescope opened its infrared eyes, it offered a new way to peek into the zone of avoidance. Its near-infrared camera, NIRCam, can see wavelengths that slip through clouds of dust that block visible light. In some of its observations toward that crowded part of the sky, JWST has revealed faint smudges of extremely distant galaxies, some of which may be connected to the outer reaches of the Great Attractor region. Their light has been traveling for hundreds of millions of years to reach us, yet even across those vast stretches, their motions line up with the same general tug. They, too, seem to be participating in the broad flow toward that gravitational basin. Across all these scales, the data keep telling one consistent story. There is a direction to our motion, and it is not random. Thinking about this can gently change the way the night sky feels. When you look up and see the scatter of stars, the hazy band of the Milky Way, and perhaps, from a dark place, the faint smudge of a distant galaxy, it's easy to imagine them as fixed points on a black canvas. But in truth, every one of those lights is in motion, falling, drifting, flowing along the unseen contours of gravity. The Milky Way is not just spinning on its own axis. It is traveling, along with its neighbors, through a universe shaped by mass it cannot fully see. We are woven into that movement. The same gravity that holds your feet to the floor is in a different register, binding planets to stars, stars to galaxies, and galaxies to superclusters. Even our most powerful telescopes cannot yet show us the full form of the Great Attractor. We infer its presence from the way it bends the paths of others, the way a hidden stone in a riverbed can be sensed by the change in the current above it. In that sense, it may be one of the most elusive structures we've ever detected, not because it hides light, but because it hides certainty. Renee Cron-Cordaweg, one of the astronomers who has spent much of her career mapping galaxies in and beyond the zone of avoidance, once put it in a way that lingers. "We are still blind to what lies beyond the dust," she said. "But gravity is not. Gravity sees what we cannot. It responds to every mass, no matter how obscured, connecting the smallest atom to the largest supercluster in a single, silent conversation. It is the one language every particle understands, the quiet rule that underlies all the visible stories of motion. So as we drift toward the Great Attractor, carried along by the flow of galaxies through the wide, dark spaces between superclusters, it can be calming to remember that our Milky Way is just one traveler among thousands. The thing pulling us is not a monster in the sense of a single, devouring object, but a curvature in space-time itself, a gravitational basin deeper than anything we can picture directly. And yet, even here, at this scale, the questions do not stop. If there is a valley in the cosmic landscape drawing us in, could there be an even broader slope beyond it? Is there something larger still shaping the motion of everything we see? a pattern that only becomes clear when we step back farther than we yet can. Whatever lies beyond that pull, it is already touching us in the most gentle way possible through the shared motion of the universe we live in. There is a strangely quiet thought that follows all this talk of hidden pools and invisible valleys in the universe. What if some of the biggest answers are sitting directly behind our own galaxy, just out of sight? For nearly a century, astronomers have known there is a region in the night sky where their instruments begin to fail. Not because the technology is weak, but because the foreground is overwhelmingly bright and messy. A part of the sky so filled with dust, gas, and starlight from the Milky Way that most ordinary telescopes simply go blind. They gave it a name that sounds almost like a metaphor, but isn't: the zone of avoidance. In simple terms, it's the broad band along the plane of our galaxy where interstellar clouds and crowded star fields block our view of what lies beyond. When you look toward the Milky Way's thickest regions, you're looking through layer upon layer of gas and dust, each one scattering and absorbing light. Behind that haze, distant galaxies are trying to shine through, but their light is softened, dimmed, and often erased before it reaches us. And this blind band is not a narrow scar. It covers nearly 20% of the entire sky. Imagine a world map with a fifth of it smudged out, an entire ocean or continent missing beneath a smear of paint. That is what our cosmic map has looked like for a long time. An enormous gap where anything could be hiding. Clusters, superclusters, or perhaps the deeper roots of the gravitational pull we feel as the Great Attractor. For decades, that blind spot sat right where our curiosity pointed. Astronomers could measure the peculiar motions of nearby galaxies and see that many of them were curving toward a region in the direction of Centaurus and Norma. They could tell that something there, something very massive, was tugging on entire clusters. But the thing itself, the structure doing the pulling, remained invisible. As NASA once put it, the Great Attractor sits behind the Milky Way's dust, a gravitational anomaly hidden from view. In the early 1980 seconds, optical telescopes were almost powerless in that direction. No matter how large the mirror or how long the exposure, the Milky Way's own stars and dust created a bright, mottled background that drowned out the faint glow of distant galaxies. Only a few types of light could slip through: radio waves with very long wavelengths, and, later, infrared light that could weave between the dust grains. So astronomers turned to radio astronomy. Using the 21-centimeter hydrogen line, a specific radio wavelength emitted by neutral hydrogen gas, astronomers at the Parkes Radio Telescope in Australia began a patient, methodical scan of the southern sky. Night after night, the dish listened to faint radio murmurs coming from beyond the Milky Way's veil. Each detection of a distant galaxy in 21-centimeter emission was like finding the edge of a shell in thick fog, a hint that something larger lay beneath the blur. By the late 1990 seconds, these radio maps began to tell a new story. The region behind the thick band of the Milky Way was not empty at all. It was crowded. Hidden galaxies emerged in the data, forming clusters and filaments that matched what gravitational theories had quietly suggested. Near the heart of what we call the Great Attractor, they identified the Norma cluster, a dense gathering of thousands of galaxies locked together by their mutual gravity. It was an exciting revelation, but also a humbling one. Even these early maps were incomplete. The deeper astronomers looked, the more they realized that the darkness in that direction was not just a curtain of dust, it was a knot of complexity. The Milky Way itself emits radio and infrared radiation, a background glow that can mask what lies beyond. Stars flicker, gas clouds shine, and all of that foreground light has to be modeled and subtracted before the faint background can be seen clearly. What lay behind remained partially uncertain, like a landscape glimpsed through overlapping reflections on glass. Things began to change more dramatically with a new generation of instruments. In 2013, ESA launched Gaia, a mission whose primary goal was to map the positions and motions of more than 1.5 billion stars in our galaxy. On the surface, it sounds like a project focused inward on the Milky Way itself. But the motions of those stars can carry hints of forces acting from beyond. If something massive outside the galaxy is tugging on the Milky Way as a whole, its influence can subtly shape the dance of stars inside it. Gaia's exquisite astrometry, its ability to measure incredibly small changes in star positions, offers indirect clues about those larger pulls. At the same time, infrared space telescopes like NASA's WISE and Spitzer began to pierce the dust in a more direct way. Infrared light, especially at longer wavelengths, can slip between the grains of interstellar dust that block visible light. Galaxies that are completely invisible in optical images can glow softly but clearly in the infrared. By combining data from these missions, astronomers started to fill in the missing parts of the sky, finding galaxies right where the zone of avoidance had once looked utterly blank. One particularly important step was the 2 Mass Redshift Survey, which used near-infrared observations to identify galaxies and then measured their redshifts to estimate distances and motions. This survey uncovered entire galaxy clusters that had never been cataloged before, hiding directly behind the galactic plane. It was like lifting a veil that had been draped over a portion of the cosmos and discovering not a void, but a crowded city of lights. Renée Kron-Korteweg, a South African astronomer who devoted decades of her career to studying galaxies in and near the zone of avoidance, once said that we are finally beginning to see through the Milky Way's dust, and what we find beyond it is extraordinary. For years, she and her colleagues had painstakingly gone through photographic plates by hand, marking faint smudges near the galactic plane, arguing that those smudges were distant galaxies, not flaws or artifacts. They worked in a kind of quiet isolation, holding on to the belief that the hidden sky contained crucial pieces of a bigger puzzle. As new surveys came online and digital detectors replaced photographic plates, much of what they had suspected began to be confirmed. The hidden regions were rich with structure, but even as the number of known galaxies in that direction grew, another problem emerged. When you add up the mass of all the visible galaxies in and around the Great Attractor region, it still isn't quite enough to explain the full strength of the gravitational pull we observe. The visible matter falls short. That gap led many researchers to a deeper conclusion. Whatever is truly pulling us may not be visible in ordinary light at all. It might be dominated by dark matter, the mysterious, invisible substance that appears to make up most of the universe's mass. Dark matter does not emit light, reflect it, or absorb it in the ways we're used to. We only know it's there because of the way its gravity acts on visible matter. In 2022, the James Webb Space Telescope added a new layer of detail. With its powerful infrared instruments, especially its near-infrared camera, JWST, can see through some of the densest dust clouds and detect extremely faint, distant galaxies. When it turned part of its attention toward regions overlapping the zone of avoidance, it picked up delicate smudges of light from galaxies whose signals had been traveling for hundreds of millions of years. Some of these newly revealed galaxies seem to line up along elongated patterns, filaments that match the structures predicted by cosmological simulations of the cosmic web, where dark matter forms a kind of invisible scaffolding. In those simulations, galaxies are like lights strung along threads of dark matter. The threads themselves are dark, but their presence is betrayed by the way the lights are arranged. ESA scientists and their collaborators now tend to speak of the Great Attractor less as a single thing and more as a direction in the flow of gravity, a region where multiple filaments and overdensities combine to create a deep valley in the gravitational landscape. In that picture, the Great Attractor is not a solitary monster, but part of a larger dark matter network stretching across the local universe. One researcher described it with a simple, soothing analogy. Imagine the universe as an ocean of invisible mass. Galaxies are like boats on the surface, their paths shaped by currents you cannot see directly. You don't see the water itself, but you see how the boats drift, how they cluster, how they are drawn into certain regions. That is how we know the currents are there. The zone of avoidance, in this metaphor, is not an empty patch of water, but a region where the waves are hard to see because of the glare, even though the currents below are as strong as anywhere else. Behind every map, every contour line showing a flow of galaxies, lies a long human story. For over 30 years, astronomers like Kron Korteweg and her colleagues spent their days and nights mapping galaxies by hand, working from photographic plates and early digital images, circling each faint blur that might be a distant world of stars. They often did this against a backdrop of skepticism. Why look where others thought there was nothing to see? But they trusted the hints in the data, the slight departures from smoothness, the quiet signs of structure in the places where the Milky Way's glow was thickest. When the first digital all-sky surveys and radio maps began to confirm their suspicions, it must have felt like the universe was whispering back, "You were right to search where no one else could see." Today, with JWST's sharp infrared vision and Gaia's precise measurements of stellar motion, that whisper has grown clearer. We now see bridges of galaxies, long filaments, and dense knots stretching through parts of the zone of avoidance, connecting the Norma cluster, the Hydra Centaurus region, and the Shapley concentration into one vast gravitational network. Our galaxy, it seems, is not being drawn by a single hidden mass, but by an entire lattice of gravity and dark matter extending over hundreds of millions of light years. Even with all this progress, the zone of avoidance remains a frontier. About 10% of the sky is still effectively hidden, even to our best infrared telescopes. In those uncharted regions, there may be new superclusters, unexpected filaments, or perhaps the deeper roots of the flows we call the Great Attractor. The universe is in no rush to reveal them. It waits while we slowly improve our instruments, refine our methods, and learn how to listen more carefully to the ways matter moves. Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you, and yet, piece by piece, it does. Slowly, through patience, precision, and the quiet persistence of people willing to stare at the same patch of sky for years, patterns emerge. Places that were once pure blankness resolve into intricate structure. So when you picture the Milky Way, a luminous river stretching across the night, it can be gentle and grounding to remember that it is also a curtain. Behind that shining band lie entire realms of galaxies, dark matter, and cosmic filaments, all shaping the motion of everything we know. The universe is not just expanding outward, it is also pulling and flowing, responding to structures we are only beginning to trace. And the zone of avoidance, once our greatest blind spot, is slowly turning into a window, a place where, by learning to see past our own galaxy's glow, we start to glimpse the deeper currents that carry us through the dark. After all this talk of hidden valleys in the cosmic web and currents we can't see, another quiet thought drifts in. If our path is being shaped by the great attractor and by long filaments of dark matter stretching between clusters, maybe Sagittarius A was never really the main anchor of our galaxy at all. Maybe the true center of the Milky Way is something we can't see directly, something larger and softer-edged, woven from invisible mass. For a long time, we pictured the Milky Way as a great spiral of stars circling a single gravitational heart, a glowing disk wrapped around a dark core, with Sagittarius A reigning at the center. It's a simple, comforting picture, but as astronomers kept measuring, kept refining, kept listening more carefully to how stars move, that picture began to feel incomplete. There is more weight in our galaxy than the light can account for, and most of it lives in the dark, surrounding every star you can see, every planet, every gas cloud, and even the central black hole itself is a vast, invisible structure, the dark matter halo. It doesn't shine, it doesn't glow, it doesn't scatter or absorb light in any way we've yet been able to detect, and yet its gravitational pull is written into the motion of almost everything. By most estimates, this ghostly framework makes up nearly 85% of our galaxy's total mass. Without it, the Milky Way wouldn't hold together. NASA once summarized it in a simple sentence: the stars in a galaxy move too fast for the galaxy to stay bound without some extra, unseen mass. If we only count the stars, gas, dust, and black holes we can detect with light, the numbers don't add up. Galaxies like ours should have spun themselves apart long ago, flinging stars off into intergalactic space like droplets cast from a spinning wheel. The fact that they do not, that their disks stay mostly intact over billions of years, is one of the strongest hints that something invisible is holding them together. The story of how we came to this realization often circles back to one person, Vera Rubin. In the 1,970 seconds, she carried out a series of quiet, careful measurements that would change our view of the universe. Rubin studied the rotation curves of spiral galaxies, how fast stars move at different distances from their centers. According to the gravity we experience in our solar system, you'd expect stars farther out to move more slowly, just as the outer planets circle the sun more slowly than the inner ones. But when Rubin and her colleagues measured those speeds, the outer stars refused to slow down. In galaxy after galaxy, the rotation curves flattened out. Stars far from the center were moving just as fast as those closer in, sometimes even faster. The visible mass, the stars and gas you could see, was nowhere near enough to explain such high speeds. Something else had to be adding gravity, not just in the bright central regions, but all the way out into the dim outskirts. Rubin's conclusion was gently radical. Each galaxy must be embedded in a huge halo of invisible matter, extending far beyond the regions that glow in starlight. What you see in a spiral galaxy, she once said, is only the frosting on the cake. The luminous disk, the spiral arms, the core, these were just the decoration, sitting atop a much larger, darker structure of mass. That insight changed everything. Today, astronomers estimate that the Milky Way's dark matter halo stretches out to at least 200,000 light-years from the center, maybe more. If you could see it, it would look like an enormous, roughly spherical cloud of gravity. with the bright spiral disk of stars floating inside it, like a thin, glowing slice. The total mass of this halo is thought to be on the order of 1 trillion times the mass of the Sun, about 10 times more than all the visible stars, gas, and dust put together. In that light, Sagittarius A, massive as it is, starts to look less like the ultimate anchor and more like a feature suspended within a much bigger framework. It is a heavy node embedded in a larger web. The true weight of the galaxy belongs to the dark halo that surrounds and permeates it. Missions like Gaia have given us some of the most detailed clues about this invisible structure. By tracking the three-dimensional motions of over 1 billion stars, Gaia has revealed subtle patterns in how they move, patterns that only make sense if there is a great deal of unseen mass shaping their orbits. In 2022, analyses of Gaia data strengthened the picture of the Milky Way, wrapped in a vast halo, extending far beyond the visible disk, its gravity guiding the paths of stars all the way out to the galaxy's edges. Even our Sun's journey, speeding around the galactic center at roughly 220 kilometers per second, is controlled far more by that hidden mass than by the stars we can see. We are swimming through an invisible sea of gravity, feeling its pull without ever seeing its surface. One way to imagine it is to picture the galaxy as a luminous jellyfish floating in a clear, dark ocean. The glowing arms of stars and gas are the visible parts, delicate tendrils trailing along. The bulk of the creature, the main body that gives it shape and weight, is nearly transparent, the dark matter halo. You only know it's there because of how everything inside it moves and how tightly it holds together. And because the ocean itself is not still, the jellyfish drifts with it, carried by currents that extend far beyond what it can sense. What's remarkable is that this drift is not just an idea, it is something we can measure. The Milky Way doesn't simply spin in place. It also moves through space as part of a broader flow of dark matter and galaxies. Our local group, the collection of galaxies that includes the Milky Way, Andromeda, and many smaller companions, is embedded in a continuous stream of dark matter. Simulations suggest that a kind of invisible bridge of mass connects the Milky Way and Andromeda, a filament along which both galaxies are slowly drawn toward each other. In large-scale computer simulations like those of the illustrious TNG project and new European missions designed to map the dark universe, the dark matter web appears as a sprawling scaffold. It's a bit like seeing the steel frame of a building, with the walls and windows and decorations yet to be added. Carlos Frank, one of the astrophysicists who helped shape our understanding of this, once described dark matter as the cosmic scaffolding on which galaxies are built. Gas falls into the gravitational wells formed by dark matter. Stars ignite within that gas. Over time, the visible parts of galaxies grow along the hidden bones of the dark web. Since we cannot detect dark matter directly, much of our knowledge comes from the way it bends light, a phenomenon called gravitational lensing. According to Einstein's general relativity, mass curves space-time, and light follows those curves. When a cluster of galaxies sits between us and even more distant background galaxies, the invisible dark matter in the cluster can distort the background light, stretching and smearing it into arcs and faint rings. In 2020, data from the Hubble Space Telescope and the Planck Observatory were combined to create maps of dark matter on cosmic scales. By observing how galaxy clusters distorted the light behind them, astronomers could trace the outlines of dark matter concentrations across the sky. The resulting maps showed long, ghostly filaments connecting clusters, like strands in a sprawling spiderweb. Our own galaxy sits within one of these strands, quietly drifting through this invisible network. When the James Webb Space Telescope started its deep field observations, it added yet another layer of insight. JWST's infrared sensitivity allowed it to see galaxies from the universe's early years, only a few 100 million years after the Big Bang. Even there, in that young cosmos, the clustering of galaxies hints at dark matter halos, already in place, tiny wells of gravity drawing gas together, seeding the first generations of stars. The same kind of invisible matter that now holds the Milky Way together was already at work long before our sun existed. Taken together, these findings gently reshape the role of Sagittarius A. The black hole we once imagined as the unmoving center isn't really a conductor directing the galaxy's motion. It's another instrument in the orchestra, following a score written mostly by dark matter. The black hole's gravity dominates its immediate neighborhood, bending the paths of nearby stars and gas. But the overall rhythm of the Milky Way's motion, the way the disk rotates, the way the galaxy travels through space, is set by the halo that surrounds it. Gaia's data even reveals small ripples in the stellar disk waves of motion that may be the fingerprints of interactions between the Milky Way's visible matter and its dark halo. Some models suggest that when smaller galaxies, like the Sagittarius dwarf spheroidal galaxy, fall into and pass through our halo, their own dark matter and stars can stir the Milky Way like a spoon in water. These encounters send waves across the disk, warping its outer edge so that it bends and flares instead of lying perfectly flat. It's as if the invisible ocean our galaxy swims in is never fully calm. Despite all this progress, dark matter itself remains one of science's most elusive mysteries. We see its gravitational handwriting everywhere, from the rotation of galaxies to the motion of clusters, from gravitational lensing to the cosmic microwave background, but we have yet to catch even a single particle of it directly. Deep underground, in quiet laboratories, shielded from cosmic rays and noise, experiments like Xenon in Italy and Lux Zeppelin in the United States are listening for the faintest possible collisions between dark matter and ordinary atoms. So far, those detectors have heard only a kind of deep silence, but that silence doesn't erase the evidence written in the sky. What the motions of galaxies and clusters tell us, again and again, is that the unseen outweighs the seen. The stars, planets, and glowing gas that we can observe are just the bright foam on top of a much deeper ocean. Neil deGrasse Tyson once remarked that we are not at the center of the universe, but part of a cosmic web, and that the web decides where everything goes. It's a simple way of saying something profound. Even the largest structures we know, the bright spirals and giant ellipticals, are passengers. They ride along paths laid down by dark matter, following curves in a gravitational landscape they did not choose. So, if you imagine the Milky Way gliding through the darkness, it can be soothing to remember that its shimmer is only a trace of what truly holds it together. The real galaxy, in the sense of total mass and structure, is far larger, far heavier, and far more mysterious than the stars we see. Sagittarius A may be our most dramatic symbol of power, but the quiet, invisible hand of dark matter is what gives it a place to orbit at all. And that realization leaves us with a softer, deeper question, one that lingers at the edge of sleep. If dark matter is what holds galaxies together, then what, in turn, holds the dark matter itself within the grand flow of the universe? If dark matter is the quiet hand guiding our galaxy, then it's natural to wonder what that hand itself rests on. When you follow the threads of gravity outward, Past the Milky Way's halo, past the local group, you arrive at a picture that is both humbling and strangely calming. Our galaxy is just one small cell in something far larger, a kind of vast, living network that stretches across the visible universe. Astronomers call this network the cosmic web. It's not a web in the way a spider spins one, with visible strands gleaming in the light. This web is made mainly of dark matter, woven into long, invisible filaments that thread through space on scales of hundreds of millions of light years. Galaxies, galaxy clusters, and superclusters gather along these filaments like dew on threads, tracing out the skeleton of the universe. Every atom, every star, every galaxy we know is sitting somewhere inside this structure, held and guided by it. Each filament can run for unimaginable distances, connecting entire clusters like gravitational tendrils stretched through the dark. Our home galaxy, the Milky Way, lives inside one of these threads. On maps, that thread is part of a larger region called Laniakea, a Hawaiian word that means immense heaven. In 2014, Brent Tully and his collaborators used the motions of more than 8,000 galaxies, along with data from NASA's Cosmic Flows surveys, to redraw our cosmic address. Before that work, we thought of ourselves as belonging to the Virgo Supercluster. Afterward, we understood that Virgo is just one basin within the broader Laniakea flow. To build that map, Tully's team didn't just look at where galaxies are, they watched how they move. By measuring redshifts, how much the light from galaxies is stretched, they could infer velocities. When you combine thousands of those velocities, you begin to see patterns, galaxies streaming along preferred directions, flowing toward common basins instead of drifting aimlessly. What they found was startling in its simplicity. Galaxies are not falling straight into single points of mass. They are flowing along gravitational currents shaped by the geometry of the web itself. Tully summed it up in one soft sentence. We are not falling into something, we are flowing. That line isn't just poetic, it is literally how the data look. For decades, we imagined galaxies as lonely islands, scattered through mostly empty space. Now, the picture is closer to a vast ocean, with galaxies as suspended particles in a gentle but persistent current, drawn inward by gravity, pushed apart by dark energy, and carried along the contours of the cosmic web. Our Milky Way seems to sit near the boundary between two large gravitational basins, the Virgo region, which our local group is moving toward, and the Hydra Centaurus region, which merges into the broader structure of Laniakea. All of this together spans on the order of 500 million light-years and contains over 100,000 galaxies. When NASA and other institutes turned these datasets into three-dimensional visualizations, they saw each galaxy moving like a drop of water in a stream, its path bending gently toward a region near the Great Attractor. That long-standing mystery, that unseen concentration of gravity, is no longer an isolated monster, but one deep valley within a continuous landscape of mass. In this view, space is not a smooth, featureless void. It has texture, it has density, it has flow. ESA's Planck satellite helped confirm this cosmic architecture by looking back to the universe's earliest light. By measuring tiny fluctuations in the cosmic microwave background, the faint afterglow of the Big Bang Planck mapped regions that were slightly denser or thinner than average in the early universe. Those small ripples in density were the seeds from which the cosmic web would grow. Over billions of years, gravity drew matter into the denser regions, stretching them into filaments and nodes, while dark energy slowly pulled the voids apart, inflating the spaces in between. When you see computer renderings of the cosmic web with its glowing threads and knots, it can be hard not to think of neural networks or delicate tissues or the branching of roots. An interconnected system that seems to breathe and evolve, pulsing slowly on timescales longer than any human era. The James Webb Space Telescope adds a particularly intimate layer to this story. In its deep field observations, JWST's infrared eyes peer back to a time only a few 100 million years after the Big Bang. In those images, astronomers can pick out early galaxies not in isolation, but already clustering along narrow lanes, filaments of gas and dark matter that match what our simulations predict. Around 350 million years after the Big Bang, these threads appear as some of the first outlines of structure, guiding where galaxies would grow, where clusters would form, and where the great basins of the future cosmic web would deepen. The distances involved are so large that even light, racing at its cosmic speed limit, takes billions of years to cross them. When you look at a cosmic web visualization, you're seeing a frozen frame from a movie that has been playing for more than 13 billion years. Behind all of this is an extraordinary level of collaboration and quiet technology. The mapping of Laniakea required careful measurements of redshifts, plus independent distance indicators, standard candles, and other methods to separate pure expansion from additional motion. Each galaxy's redshift tells you part of the story, how fast it's moving away due to the universe's expansion. But small deviations from that smooth pattern, the peculiar velocities, reveal the gravitational pulls and pushes of nearby structures. When thousands of these measurements are combined and processed through sophisticated statistical tools, flow lines begin to appear. In visualizations created by NASA and the Institut de Physique du Globe de Paris, you can see those flow lines rippling and curving like ocean currents, converging on deep gravitational trenches. It doesn't look random. It looks like choreography, gravity, performing a slow dance across billions of light years. What's perhaps most remarkable is how coherent these flows are over vast distances. Galaxies separated by hundreds of millions of light years still share common directions of motion, like dancers moving in patterns they cannot see, bound by a tension that stretches far beyond any individual cluster. Large-scale simulations, like the illustrious TNG and Millennium projects, recreate this behavior in virtual universes. Starting from early density ripples similar to those seen by Planck, they let dark matter and gas evolve under gravity and expansion. The result is a web of filaments and nodes, whose flowing motions closely resemble what we measure in the real sky. Some astronomers liken this to the universe having a kind of pulse, not a simple heartbeat, but a balance between two long, slow forces: gravity, which pulls matter together into clusters and filaments, and dark energy, which pushes space itself to expand faster and faster. In dense regions, gravity wins for a while, growing structures. In the voids, dark energy takes the lead, stretching space and deepening the emptiness. The structure of the universe is written in that tug-of-war. To study this balance quantitatively, researchers use features called baryon acoustic oscillations, faint sound waves, from the early universe that left ripples in the distribution of matter. These ripples act like a cosmic measuring stick by comparing their apparent size at different times using galaxy surveys. Missions such as ESA's Euclid and instruments like the Dark Energy Spectroscopic Instrument are tracing how the cosmic web has stretched. Their data will help refine how we think dark matter and dark energy share the work of shaping the universe. Every new dataset reinforces the same quiet reminder: our galaxy is not resting. The Milky Way moves through Laniakea, and Laniakea itself moves within an even larger network of filaments that extend to the edge of the observable universe. We are drifting through a gravitational sea whose currents were already in motion long before the sun was born. The idea that the universe flows rather than simply falls is one of the gentlest and most elegant shifts in modern cosmology. When Brent Tully said, "We are not falling into something, we are flowing," he was describing more than a feeling. He was describing the way gravity and expansion work together to create paths through space. Paths our galaxy, our local group, and every cluster we can see are quietly following. Within that flow, the Milky Way doesn't orbit a single, special point. It drifts along the strands of the web, carried by the shape of dark matter and the broad expansion of the universe. Even closer to home, Gaia's latest data releases allow astronomers to trace streams of stars and small satellite galaxies around the Milky Way. Many of these smaller motions line up with the broader cosmic directions, hinting that even local patterns are, in some softened way, echoes of the larger flow. For many scientists, this picture has brought not just answers, but a sense of humility. Carl Sagan once said that the universe is not required to be in harmony with human ambition. And yet, when you look at these maps and simulations, harmony is exactly what you see. Orbits nested within orbits, flows within flows, all part of a single, continuous rhythm. So when you imagine the Milky Way drifting through space tonight, it might be comforting to remember that it isn't traveling alone or at random. It moves within a web that spans the universe, a structure that connects us to every galaxy, every cluster, every point of light you've ever seen. The cosmic web doesn't only hold us in place, it gently, steadily carries us along. Even this idea of a vast web carrying galaxies along its threads leaves one more question quietly glowing underneath. If we are flowing, what sets the direction of that flow? What invisible current tells not just galaxies, but space itself how to move? It sounds like there ought to be a simple answer. For so long, we pictured the cosmos as a great whirlpool, stars orbiting the centers of galaxies, galaxies orbiting within clusters, clusters drifting around some deeper center. Motion felt like it should always be around something, as if there must be a cosmic middle, an ultimate anchor. But when astronomers looked carefully at the universe on the largest scales, that expected center never appeared. No special point showed up in the maps, no place where everything seemed to be orbiting around. Instead, they found one of the most counterintuitive truths in physics. The universe has no center, and yet everything moves. What we call motion, when we talk about galaxies racing away from each other, is not a dance around a central point. It is the stretching of space itself. In the early 20th century, Edwin Hubble studied the light from distant galaxies with the Hooker telescope on Mount Wilson. He noticed that their light was redshifted, stretched toward longer wavelengths. The farther away a galaxy was, the more its light was shifted. When he plotted distance against this redshift, a simple pattern emerged. Far galaxies receded faster. This relation became known as Hubble's law. At first, it might have been tempting to imagine galaxies just flying apart through a static space. But as the math of general relativity settled in and more data arrived, a subtler picture took shape. It's not that galaxies are rushing through a fixed void. It's that the void itself, the grid of space-time, is stretching, carrying the galaxies along. NASA likes to explain it with a simple image. It isn't galaxies moving through space, it's space moving around the galaxies. One common way to imagine this is a loaf of raisin bread rising in the oven. The dough is space. The raisins are galaxies. As the dough expands, every raisin moves away from every other raisin. No raisin is at a privileged spot. Each one could say, honestly, everything is receding from me, and each would be correct. There is no single raisin that marks the center of the loaf. The same is true of the universe. On large scales, space expands uniformly. There isn't an edge where the expansion starts, and there isn't a central point from which everything flies outward. The expansion happens everywhere at once. The cosmic microwave background, the faint afterglow of the Big Bang, adds another layer of reassurance. Satellites like COBE, WMAP, and Planck have mapped this radiation across the entire sky. What they see is astonishingly uniform. Tiny temperature variations, 1 part in 100,000, dot the sky. But overall, the pattern looks the same in every direction. There is no spot that screams, here is the center. This uniformity, or isotropy, tells us that there is no special vantage point. From the Milky Way, from a galaxy billions of light years away, the view of the universe's early light would be similarly even. Stephen Hawking once said that the universe is expanding not into anything, but from itself. The sentence sounds almost like a riddle, but it's just the geometry of space-time. Space doesn't need an outside container. It defines its own shape. Another image that helps is the surface of a balloon being inflated. Imagine tiny dots on that surface, representing galaxies. As you blow up the balloon, every dot moves away from every other dot. But none of the dots sits at the center of the surface. The center of expansion is somewhere in the space around the balloon, in a dimension the dots cannot access. For the dots, there is only the surface, and on that surface, there is no special center. Our universe behaves similarly, but in 3 dimensions of space instead of 2. So the cosmic web we talked about earlier, the filaments, clusters, and voids, is laid out on an expanding balloon of space. The flows of galaxies toward regions like the Great Attractor, the drift of our local group through Laniakea, all happen within this larger expansion. Locally, gravity creates flows and orbits. Globally, space stretches, and everyone moves apart on average. Missions like ESA's Gaia and NASA's James Webb Space Telescope sharpen this picture. Gaia maps the positions and motions of more than 1 billion stars, while Webb peers deeply into the early universe. Together with galaxy surveys and supernova observations, they confirm that the Hubble flow, the overall expansion, remains smooth and uniform on large scales. Yes, galaxies gather into clusters under gravity. Yes, some fall toward each other, like the Milky Way and Andromeda, slowly spiraling together. But on the biggest scales we can see, the expansion looks remarkably even. And that expansion is not just continuing, it is speeding up. In 1998, 2 independent teams studying distant Type Ia supernovae standard candles used to measure cosmic distances found something unexpected. Instead of slowing down under the mutual pull of gravity, the expansion of the universe seemed to be accelerating. Galaxies were not just receding, their recession velocities were increasing faster than anyone anticipated. To name this unknown cause, scientists reached for a simple phrase: dark energy, a kind of energy built into space itself, acting as a gentle, persistent pressure that pushes the universe to expand more and more rapidly. Current estimates suggest that dark energy accounts for nearly 70% of the universe's total energy content. It doesn't clump like matter. It doesn't form halos or filaments. It simply appears as a property of the vacuum, influencing the overall behavior of space-time. In NASA's words, dark energy is the name we give to whatever is causing the accelerated expansion. We don't yet know its true nature, only its effect. The stretching of the cosmic web is speeding up. That means every filament, every cluster, every galaxy is being carried along by an expansion that is growing faster over time. The flows toward attractors and basins ride on top of this stretching. Galaxies don't orbit a grand central point because there isn't one. Their motion is a mixture of local gravity and global geometry, written in Einstein's equations. General relativity, Einstein's theory from 1915, sits quietly underneath all of this. It says that matter and energy tell space-time how to curve, and curved space-time tells matter how to move. If you fill a universe evenly with matter and energy, and let Einstein's equations describe its fate, the most natural outcome is not a static cosmos, but one that changes size, usually expanding or contracting. Einstein himself initially tried to force a static solution by adding a cosmological constant, but later called that his biggest blunder when observations favored expansion. The remarkable part is that the math doesn't just describe motion, it requires it. In a universe like ours, expansion is not an afterthought, it is built in. One of the strangest consequences of this is that, in a certain sense, you are always at the center. So is every other point. Because the expansion is uniform, any observer in any galaxy sees other distant galaxies receding roughly according to the same rule. From their perspective, they too are at the middle of the Hubble flow. This apparent paradox dissolves when you remember the raisin bread or the balloon. Each raisin, each dot, can claim to be central and still not be special. ESA's Euclid mission, launched to study dark matter and dark energy, is now mapping billions of galaxies to see exactly how this expansion has changed over cosmic time. Its instruments measure the subtle imprint of dark energy on the cosmic web, how filaments grew, how voids stretched, how the overall expansion rate evolved. Early results suggest that the expansion is incredibly smooth, varying by less than a tiny fraction of a percent across the observable universe. On these scales, space-time behaves with astonishing uniformity. Behind the acronyms and numbers is a gentle, profound idea. There is no place in the universe that can truly claim to be at rest. No cosmic rock to stand on that isn't itself being carried along. The Milky Way, our local group, our supercluster, all participate in this quiet unfolding. What we feel as motion is not a voyage around a central lighthouse, but the simple fact that the fabric we inhabit is stretching. Astronomers call this the metric expansion of space. It's not like a wave you could surf or a wind you could feel. It is a change in the way distances are measured by the geometry of space-time itself. Because of this, galaxies beyond a certain distance appear to recede from us, faster than the speed of light. They're not breaking Einstein's speed limit. No galaxy is zooming through space at that speed locally. Instead, space between us and them is expanding so quickly that light emitted now will never catch up. There is no edge, no outside region into which the universe is expanding, just an unbounded, self-contained stretching, governed by laws that, as far as we can tell, operate the same everywhere. Even the rate of that stretching, the Hubble constant, is a story in motion. Different methods of measurement give slightly different values. Observations of nearby galaxies and supernovae suggest a rate of around 73 kilometers per second per megaparsec. Measurements based on the cosmic microwave background and early universe physics suggest around 67 kilometers per second per megaparsec. The disagreement known as the Hubble tension, might be a sign that our picture still has missing pieces, or that dark energy behaves in ways we haven't fully grasped. Yet, even within these uncertainties, the outline remains steady. The universe expands, with no center and no edge, its pace subtly tuned by the interplay of matter, and dark energy. If you think of this expansion in a quiet moment, try not to picture galaxies racing through a static void. Instead, imagine a gentle, global stretching of a grid you cannot see, an invisible tide that lifts everything at once. Light, matter, gravity, all of it is carried along. The farther away you look, the more of that stretching you see, until beyond a certain distance, the recession becomes so fast that those galaxies slip forever out of view. Carl Sagan once said that we are the universe knowing itself. In this context, that knowing includes a kind of self-awareness of motion, the realization that there is no absolute stillness to return to, no grand cosmic center to rest upon. There is only participation in the expansion. So tonight, if you picture the Milky Way drifting through the dark, it may be soothing to remember that it isn't orbiting anything in the ultimate sense. It is simply one small ripple in a fabric that never stops stretching, carried along by the same quiet rules that govern every other point in space. And tucked inside that realization is a softer, deeper question, one we're only just beginning to form. If space itself can move, stretch, and carry galaxies with it, could this fabric be shaped by forces or patterns, even more subtle features of reality we've only started to glimpse at the edge of our understanding? By now, it starts to feel as if our place in the universe is less like standing somewhere and more like floating inside a moving pattern. And that thought leads to a strange, almost unsettling question. What if nothing in the universe is really moving in the way we first imagined? And it's only space itself that shifts and flows beneath everything? It sounds impossible at first, almost like a word trick. But when physicists looked closely at how galaxies, planets, and even beams of light behave, they found something deeper than simple pushing and pulling. What we call motion might just be the way the universe bends and stretches around us. This idea comes straight from Albert Einstein's general theory of relativity, published in 1915. Before that, gravity was thought of as a force acting at a distance, an invisible hand reaching out from one object to another. Einstein replaced that picture with something quieter and more geometric. He realized that space and time are not separate. Together they form a single connected fabric called space-time. And that fabric can curve. Wherever matter or energy exists, the geometry of space-time changes. Mass does not just sit in space. It tells space how to shape itself. In turn, that shaped space tells matter where and how to move. In Einstein's simple, beautiful phrasing, space-time tells matter how to move, and matter tells space-time how to curve. Once you accept that, the ordinary motions we live with begin to look different. In this picture, a planet doesn't orbit the sun because the sun is tugging on it with an invisible rope. Instead, the sun's mass curves the space-time around it, and the planet follows the straightest possible path through that curved geometry. In flat space, a straight path is a straight line. In curved space, a straight path can loop and circle. The planet is not being yanked. It is gliding along the natural lines of the universe. The same is true for stars around a galaxy, for galaxies in a cluster, and even for light itself. Light always moves along the straightest possible paths in space-time. But if space-time is bent, those paths bend too. Nothing has to push the light, the shape of the universe quietly guides it. We can actually see this happen. ESA's Gaia mission and NASA's Hubble Space Telescope have observed a phenomenon called gravitational lensing. When light from a distant galaxy passes near a massive object, like a cluster of galaxies or a heavy lump of dark matter, its path curves. The distant galaxy appears distorted, stretched into arcs, or smeared into rings. This isn't a trick of the telescope. It's space-time itself acting as a lens, bending light as it flows through the curved geometry. The object in the middle doesn't reach out and shove the light. The light simply follows the landscape that already exists. Even Sagittarius A, the supermassive black hole at the Milky Way's center, fits into this same quiet picture. It is not a solid anchor nailed into space. It sits inside the galaxy's curved space-time, which is shaped by billions of stars, clouds of gas, and the deep, invisible weight of dark matter. Every orbit around it, every tiny wobble of nearby stars, is just geometry being traced out. From the perspective of relativity, there is no force pulling those stars in the old sense, only the contour of space-time guiding their paths. When the Event Horizon Telescope collaboration released the first image of Sagittarius A, they were not capturing a thing in the way we'd photograph a rock or a planet. What they showed us was a dark shadow against a hot, glowing background, a place where the curvature of space-time is so extreme that light itself can be trapped in orbit or pulled inward beyond return. That hazy ring and dark center are geometry made visible, the outline of where space-time bends light into a swirl. And even that geometry is not fixed. As gas falls in, as magnetic fields twist, as matter moves and energy flows, the shape of space-time adjusts. The black hole's environment is like a deep, flexible well in a soft sheet, not a rigid hole in stone. The more we measure, the more it looks as if motion itself might be partly an illusion of perspective. We see planets and stars tracing paths, but what's really changing may be the underlying fabric they ride on. Another line of evidence comes from gravitational waves, ripples in space-time that spread outward when massive objects like black holes or neutron stars collide. In 2015, the LIGO observatories recorded the first direct detection of such waves, from two black holes merging more than 1 billion light-years away. The signal that reached Earth was incredibly faint. It changed the distance between mirrors in LIGO's arms by less than 1,000th of the width of a proton. Yet that tiny stretch and squeeze carried a breathtaking message. Space-time is not static. It can ripple, flex, and carry energy across the cosmos. These waves do not push objects like wind. They gently alter the distances between them. When a gravitational wave passes, it's not that the mirrors move through space. Rather, the space between the mirrors momentarily lengthens and shortens. In a quiet, technical sense, space-time itself is breathing. Future missions, like ESA's LISA, a space-based gravitational wave observatory, are designed to listen to even deeper, slower waves, those produced by supermassive black holes spiraling together, and perhaps by events from the early universe itself. When those ripples roll through our part of the cosmos, they will again stretch and compress space-time, changing distances ever so slightly, not because objects are pushing each other around, but because the fabric beneath them is shifting. The expansion of the universe, the Hubble flow, is another face of the same story. On vast scales, galaxies are not racing like bullets through a fixed emptiness. The emptiness itself is expanding. The metric, the way space-time measures distance, grows with time. Every second, on average, the space between far-flung galaxy clusters increases. We do not orbit the universe, we drift with its stretching. In this view, the universe is not a collection of separate parts moving through a static arena. It is a single, dynamic fabric in which curvature, ripples, and expansion are all aspects of one ongoing motion. Missions like Euclid are now mapping how this fabric behaves across cosmic time. By observing billions of galaxies, Euclid measures how dark matter and dark energy sculpt space-time's curvature. Each galaxy becomes a marker, showing where the geometry is deeper or shallower, denser or more open. Subtle patterns in galaxy positions and shapes can reveal how space has stretched and bent over billions of years. Some early analyses suggest that this stretching may not be perfectly uniform, that on very large scales there are gentle tides in space-time, shaped by where matter and dark energy are most concentrated. Einstein's field equations sit at the center of all this. They are the rules that link geometry to content. They tie the curvature of space-time to the density and pressure of matter and energy. Change the matter, and the curvature must change. Change the curvature, and the motion of matter responds. It's a feedback loop on the grandest scale. Matter and space-time are not separate components. They are partners in an endless exchange. Seen in that light, an orbit stops looking like a circular journey around a point and starts looking like a path carved by geometry itself. The Earth does not fall around the Sun in the way we once imagined. It follows the straightest possible track through the curved space-time created by the Sun's mass. The Sun moves through the curvature created by the Milky Way. The Milky Way drifts through the curvature created by the cosmic web and the expanding universe. Each layer of motion is really a layer of geometry. Stillness, too, changes its meaning. There is no perfectly static place in the universe, because even if you pick coordinates in which an object seems at rest, the space-time under it continues to evolve, stretching with cosmic expansion, rippling with passing waves, responding to shifts in mass and energy. Even the particles in your body are being carried forward by the same deep currents that carry stars and galaxies. You are not outside the flow, you're woven into it. Einstein's mathematics first hinted at this. Today, instruments like LIGO, Virgo, Kagra, Gaia, Hubble, JWST, and many others are watching it unfold in real time. They see light bending around mass. They feel waves of space-time passing by. They trace the paths of stars responding to an invisible geometry. From this perspective, Sagittarius A looks less like a fixed anchor and more like a buoy on a moving sea. It drifts within the Milky Way's curved space-time, just as the Milky Way drifts within the curvature of the cosmic web. Even the heart of our galaxy is being carried by the same tide that carries you. So when you look up at the night sky and your mind at the stars, the planets, the faint smear of the Milky Way, and imagine everything in motion, it's gentle to remember that you're already part of that motion. You're not circling some final center. You're inside the flow itself, riding the vast, curved fabric of space-time. As one NASA summary put it, the universe doesn't expand into space. Space expands with the universe. In a way, that might be the real orbit we all share, not just the path of stars around a black hole, but the shared journey of all things carried together through a living, shifting fabric. Even the heart of the galaxy trembles with that same current. And tonight, so do you, in your own quiet way. If this soft journey has brought you even a moment of calm or comfort, I'm quietly grateful you chose to spend this time here. A gentle like or a soft tap on subscribe is the kindest way to let me know. These night stories are keeping you company, and it helps them drift out to others who might need a bit of quiet too. And if you'd like to share, Tell me where in the world you're listening from. I love knowing where these sleepy explorations find a home. For now, may the universe carry you gently through its endless motion. May your night be peaceful, your dreams be kind, and may you feel, somewhere deep inside, the soft cradle of space-time holding you until the next story begins.